In this last lecture of this unit, we continue with some of our earlier themes and then introduce one new notion, the notion of independence of random variables. We will start by elaborating a bit more on the subject of conditional probability mass functions. We have already discussed the case where we condition a random variable on an event. Here, we will talk about conditioning a random variable on another random variable. And we will develop yet another version of the total probability and total expectation theorems. There are no new concepts here, just new notation. I should say, however, that notation is important because it guides you on how to think about problems in the most economical way. The one new concept that we will introduce is the notion of independence of random variables. It is actually not an entirely new concept. It is defined more or less the same way as independence of events and has a similar intuitive interpretation. Two random variables are independent if information about the value of one of them does not change your model or beliefs about the other. On the mathematical side, we will see that independence leads to some additional nice properties of means and variances. We will conclude this lecture and this unit on discrete random variables by considering a rather difficult problem, the hat problem. We will see that by being systematic and using some of the tricks that we have learned, we can calculate the mean and variance of a rather complicated random variable.
We have already introduced the concept of the conditional PMF of a random variable x given an event A. We will now consider the case where we condition on the value of another random variable y. That is, we let A be the event that some other random variable y takes on a specific value, little y. In this case, we are talking about a conditional probability of the form shown here. It's the conditional probability that x takes on a specific value, given that the random variable y takes on another specific value. And we use this notation to indicate those conditional probabilities. As usual, the subscripts indicate the situation that we're dealing with. That is, we're dealing with a distribution of the random variable x, and we're conditioning on values of the other random variable y. Using the definition now of conditional probabilities, this can be written as the probability that both events happen divided by the probability of the conditioning event. We can turn this expression into PMF notation, and this leads us to this definition of conditional PMFs. The conditional PMF is defined to be the ratio of the joint PMF, this is the probability that we have here, by the corresponding marginal PMF, and this is the probability that we have here. Now remember that conditional probabilities are only defined when the conditioning event has a positive probability, when this denominator is positive. Similarly, the conditional PMF will only be defined for those little y that have positive probability of occurring. Now, the conditional PMF is a function of two arguments, little x and little y. But the best way of thinking about the conditional PMF is that we fix the value little y and then view this expression here as a function of x. As a function of x, it gives us the probabilities of the different x's that may occur in the conditional universe. And these probabilities must, of course, sum to 1. Again, we're keeping y fixed. We live in a conditional universe where y takes on a specific value. And here we have the probabilities of the different x's in that universe, and these sum to 1. Note that if we change the value of little y, we will of course get a different conditional PMF for the random variable x. So what we're really dealing with in this instance is that we have a family of conditional PMFs, one conditional PMF for every possible value of little y, and for every possible value of little y, we have a legitimate PMF whose values add to 1. Let us look at an example. Consider the joint PMF given in this table. Let us condition on the event that y is equal to 2. Which corresponds to this row in the diagram. We need to know the value of the marginal at this point. So we start by calculating the probability of y at value 2. And this is found by adding the entries in this row of the table. And we find that this is 5/20. Then we can start calculating entries of the conditional PMF. So, for example, the probability that x takes on the value of 1, given that y takes the value of 2, it is going to be this entry, which is 0, divided by 5/20, which gives us 0. We can find the next entry, the probability of x taking the value of 2, given that y takes the value of 2, will be this entry 1/20 divided by 5/20, so it's going to be 1/5. And we can continue with the other two entries, and we can actually even plot the result once we are done. And what we have is that at 1 we have a probability of 0. At 2 we have a probability of 1/5. At 3 we have a probability of 3/20 divided by 5/20, which is 3/5. And at 4 we have again a probability of 1/5. So what we have plotted here is the conditional PMF. It's a PMF in the variable x, where x ranges over the possible values, but where we have fixed the value of y to be equal to 2. Now we could have found this conditional PMF even faster without doing any divisions by following an intuitive argument that we have used before. We live in this conditional universe. We have conditioned on y being equal to 2. The conditional probabilities will have the same proportions as the original probabilities, except that they need to be scaled so that they add to 1. So they should be in the proportions of 0, 1, 3, 1. And for these to add to 1, we need to put everywhere a denominator of 5. So the proportions are indeed 0, 1, 3, and 1. Pictorially, the conditional PMF has the same form as the corresponding slice of the joint PMF, except, again, that the entries of that slice are renormalized so that the entries add to 1. And finally, an observation. We can take the definition of the conditional PMF and turn it around by moving the denominator to the other side and obtain a formula which is a version of the multiplication rule. The probability that x takes a value little x and y takes a value little y is the product of the probability that y takes this particular value times the conditional probability that x takes on the particular value little x, given that y takes on the particular value little y. We also have a symmetrical relationship if we interchange the roles of x and y. As we discussed earlier in this course, the multiplication rule can be used to specify probability models. One way of modeling two random variables is by specifying the joint PMF. But we now have an alternative, indirect way using the multiplication rule. We can first specify the distribution of y and then specify the conditional PMF of x for any given value of little y. and this completely determines the joint PMF, and so we have a full probability model. We can also provide similar definitions of conditional PMFs for the case where we're dealing with more than two random variables. In this case, notation is pretty self-explanatory. By looking at this expression here, you can probably guess that this stands for the probability that random variable x takes on a specific value, conditional on the random variables y and z taking on some other specific values. Using the definition of conditional probabilities, this is the probability that all events happen divided by the probability of the conditioning event, which in our case is the event that y takes on a specific value and simultaneously z takes another specific values. In PMF notation, this is the ratio of the joint PMF of the three random variables together divided by the joint PMF of the two random variables y and z. As another example, we could have an expression like this, which again stands for the probability that these two random variables take on specific values, conditional on this random variable taking on another value. Finally, we can have versions of the multiplication rule for the case where we're dealing with more than two random variables. Recall the usual multiplication rule for three events happening simultaneously. Let us apply this multiplication rule for the case where the event A stands for the event that the random variable x takes on a specific value. Let B be the event that y takes on a specific value, and C be the event that random variable z takes on a specific value. Then we can take this relation, the multiplication rule, and translate it into PMF notation. The probability that all three events happen is equal to the product of the probability that the first event happens. Then we have the conditional probability that the second event happens, given that the first happened, times the conditional probability that the third event happens, this one, given that the first two events have happened. We will now talk about conditional expectations of one random variable given another. As we will see, there will be nothing new here, except for old results, but given in new notation. Any PMF has an associated expectation, and so conditional PMFs also have associated expectations, which we call conditional expectations. We have already seen them for the case where we condition on an event A. The case where we condition on random variables is exactly the same. We let the event A be the event that y takes on a specific value, and then we calculate the expectation using the relevant conditional probabilities, those that are given by the conditional PMF. So the conditional expectation of x, given that y takes on a certain value, is defined as the usual expectation, except that we use the conditional probabilities that apply given that y takes on a specific value, little y. Recall now the expected value rule for ordinary expectations, and also the expected value rule for conditional expectations given an event, something that we have already seen. Now, in PMF notation, the expected value rule takes a similar form. The event A is replaced by the specific event that y takes on a specific value, and in that case, the conditional PMF given the event A is just the conditional PMF given that random variable y takes on a specific value, little y. For the case where we condition on events, we also developed a version of the total probability theorem and the total expectation theorem. We can do the same when we condition on random variables. So suppose that the sample space has been partitioned into n disjoint scenarios. The total probability theorem tells us that the probability of the event that random variable x takes on a value little x, can be found by taking the probabilities of this event under each one of the possible scenarios and then weighing those probabilities according to the probabilities of the different scenarios. Now suppose that we are dealing with a random variable that takes values in a set consisting of n elements. And let us consider scenarios. AI, the ith scenario, is the event that the random variable y takes on the ith possible value. We can apply the total probability theorem to this situation. We can find the probability that the random variable x takes on a certain value little x by considering the probability of this event happening under each possible scenario, where a scenario is that y took on a specific value, and then weigh those probabilities according to the probabilities of the different scenarios. The story with the total expectation theorem is similar. We know that an expectation can be found by taking the conditional expectations under each one of the scenarios and weighing them according to the probabilities of the different scenarios. Again, let the event that y takes on a specific value be a different scenario, and with this correspondence, we obtain the following version of the total expectation theorem. We have a sum of different terms, and each term in the sum is the probability of a given scenario times the expected value of x under this particular scenario. At this point, I have to add a comment of a more mathematical flavor. We have been talking about the partition of the sample space into finitely many scenarios. But if y takes on values in a discrete but infinite set, for example, if y can take on any integer value, the argument that we have given is not quite complete. Fortunately, the total probability theorem and the total expectation theorem, they both remain true even for the case where y ranges over an infinite set, as long as the random variable x has a well-defined expectation. For the total probability theorem, the proof for the general case can be carried out without a lot of difficulty, just using the countable additivity axiom. However, for the total expectation theorem, it takes some harder mathematical work, and this is beyond our scope. But we will just take this fact for granted, that the total expectation theorem carries over to the case where we're adding over an infinite sequence of possible values of y. In the rest of the course, we will often use the total expectation theorem, including in cases where y ranges over an infinite discrete set. In fact, we will see that this theorem is an extremely useful tool that can be used to divide and conquer complicated models. We now come to a very important concept, the concept of independence of random variables. We are already familiar with the notion of independence of two events. We have the mathematical definition, and the interpretation is that conditional probabilities are the same as unconditional ones. Intuitively, when you are told that B occurred, this does not change your beliefs about A, and so the conditional probability of A is the same as the unconditional probability. We have a similar definition of independence of a random variable and an event A. The mathematical definition is that events A and the event that x takes on a specific value, that these two events are independent in the ordinary sense. So the probability of both of these events happening is the product of their individual probabilities. But we require this to be true for all values of little x. Intuitively, if I tell you that A occurred, this is not going to change the distribution of the random variable x. This is one interpretation of what independence means in this context. And this has to be true for all values of little x. That is, when event occurs, the probabilities of any particular little x is going to be the same as the original unconditional probability. We also have a symmetrical interpretation. If I tell you the value of x, then the conditional probability of event A is not going to change. It's going to be the same as the unconditional probability. And again, this is going to be the case for all values of x. So no matter what I tell you about x, your beliefs about A are not going to change. We can now move and define the notion of independence of two random variables. The mathematical definition is that the event that x takes on a value little x and the event that y takes on a value little y, these two events are independent, and this is true for all possible values of little x and little y. In PMF notation, this relation here can be written in this form, and basically the joint PMF factors out as a product of the marginal PMFs of the two random variables. Again, this relation has to be true for all possible little x and little y. What does independence mean? When I tell you the value of y, and no matter what value I tell you, your beliefs about x will not change, so that the conditional PMF of x given y is going to be the same as the unconditional PMF of x. And this has to be true for any values of the arguments of these PMFs. There is also a symmetric interpretation, which is that the conditional PMF of y given x is going to be the same as the unconditional PMF of y. We have the symmetric interpretation because, as we can see from this definition, x and y have symmetric roles. Finally, we can define the notion of independence of multiple random variables by a similar relation. Here, the definition is for the case of three random variables, but you can imagine how the definition for any finite number of random variables will go. Namely, the joint PMF of all the random variables can be expressed as the product of the corresponding marginal PMFs. What is the intuitive interpretation of independence here? It means that information about some of the random variables will not change your beliefs, the probabilities, about the remaining random variables. Any conditional probabilities and any conditional PMFs will be the same as the unconditional ones. In the real world, independence models situations where each of the random variables is generated in a decoupled manner, in a separate probabilistic experiment. And these probabilistic experiments do not interact with each other and have no common sources of uncertainty. Let us now consider a simple example. Let random variables x and y be described by a joint PMF, which is the one shown in this table. Question: are x and y independent? We can try to answer this question by using the definition of independence, but it is actually more instructive to proceed in a somewhat more intuitive way. We look at this table and we observe that a value of 1 is possible for x. In particular, the probability that x takes the value of 1, this is the marginal probability. This can be found by adding the probabilities of all the outcomes in this column, which in this case is 3 over 20. Suppose now that somebody tells you the value of y. For example, I tell you that y happens to be equal to 1, in which case you're transported into this universe. In this universe, the conditional probability that x takes a value of 1, given that y takes a value of 1, what is it? In this universe, there's zero probability associated to this outcome, so this probability is 0, which is different than 3 over 20. And since these two numbers are different, this means that information from y changes our beliefs about what's going to happen to x, and so we do not have independence. So again, intuitively, in the beginning we thought that x equal to 1 was possible, but information given by y, namely that y is equal to 1, tells us that actually x equals to 1 is impossible. Information about y changed our beliefs about x, so x and y are dependent. Now, when we first introduced the notion of independence some time ago, we also introduced the notion of conditional independence. And we said that conditional independence is the same as ordinary independence, except that it would be applied to a conditional universe. Something similar can be done for the case of random variables as well. So suppose, for example, that someone tells us that the outcome of the experiment was such that it belongs to this blue set. This is the set where x is less than or equal to 2 and y is larger than or equal to 3. So we are given this information, and this is now our new conditional model. The question is, within this new conditional model, are random variables x and y independent? Let us write down the conditional model, where I'm only showing the 4 possible outcomes that are allowed in the conditional model. All the others, of course, will have 0 probability in the conditional model. So in the conditional model, probabilities will keep the same proportions as in the unconditional model, and the proportions are 1, 2, 2, 4, but then they need to be scaled or normalized so that they add to 1. And to make them add to 1, we need to divide them all by 9. In this conditional model, this is the joint PMF of the two random variables x and y. Let us find the marginal PMFs. To find the marginal PMF of x, we add the entries in this column, and we get here 1/3 and here 2/3. And to find the marginal PMF of y, we add the entries in this column to find 2/3. And we add the entries in that column to find 1/3. So this is the marginal PMF of x, that's the marginal PMF of y. And now we notice that this entry of the joint PMF is 1/3 times 1/3, the product of the marginals. This entry is the product of 1/3 times 2/3, the product of the marginals, and so on for the remaining entries. So each entry of the joint PMF is equal to the product of the corresponding entries of the marginal PMFs, and this is the definition of independence. So in this conditional blue universe, we do have independence, and the way that this was established was to check that the joint PMF factors as a product of marginal PMFs. When we have independence, does anything interesting happen to expectations? We know that in general the expected value of a function of random variables is not the same as applying the function to the expected values. And we also know that there are some exceptions where we do get equality. This is the case where we are dealing with linear functions of one or more random variables. Note that this last property is always true and does not require any independence assumptions. When we have independence, there is one additional property that turns out to be true. The expected value of the product of two independent random variables is the product of their expected values. Let us verify this relation. We are dealing here with the expected value of a function of random variables, where the function is defined to be the product function. So to calculate this expected value, you can use the expected value rule, and we are going to get the sum over all x, the sum over all y of g of xy, but in this case g of xy is x times y, and then we weigh all those values according to the probabilities as given by the joint PMF. Now, using independence, this sum can be changed into the following form. The joint PMF is the product of the marginal PMFs. And now when we look at the inner sum over all values of y, we can take outside the summation those terms that do not depend on y, and so this term and that term, and this is going to yield a summation over x of x times the marginal PMF of x, and then the summation over all y of y times the marginal PMF of y. But now we recognize that here we have just the expected value of y, and then we will be left with another expression, which is the expected value of x. And this completes the argument. Now consider a function of x and another function of y. X and y are independent. Intuitively, the value of x does not give you any new information about y, so the value of g of x does not give you any new information about h of y. So on the basis of this intuitive argument, the functions g of x and h of y are also independent of each other. Therefore, we can apply the fact that we have already proved, but with g of x in the place of x and h of y in the place of y. And this gives us this more general fact, that the expected value of the product of two functions of independent random variables is equal to the product of the expectations of these functions. We could also prove this property directly without relying on the intuitive argument. We could just follow the same steps as in this derivation. Wherever there's an x, we would write g of x, and wherever there is a y, we would write h of y, and the same algebra would go through, and we would end up with the expected value of g of x times the expected value of h of y. Let us now revisit the variance and see what happens in the case of independence. Variances have some general properties that we have already seen. However, since we often add random variables, we would like to be able to say something about the variance of the sum of two random variables. Unfortunately, the situation is not so simple, and in general, the variance of the sum is not the same as the sum of the variances. We will see an example shortly. On the other hand, when x and y are independent, the variance of the sum is equal to the sum of the variances. And this is a very useful fact. Let us go through the derivation of this property, but to keep things simple, let us assume, just for the sake of the derivation, that the two random variables have zero mean. So, in that case, the variance of the sum is just the expected value of the square of the sum. And we can expand the quadratic and write this as expectation of x squared plus 2xy plus y squared. Then we use linearity of expectations to write this as expected value of x squared plus twice the expected value of x times y, and then plus the expected value of y squared. Now, the first term is just the variance of x, because we have assumed that we have zero mean. The last term is similarly the variance of y. How about the middle term? Because of independence, the expected value of the product is the same as the product of the expected values, and the expected values are zero in our case. So this term, because of independence, this term is going to be equal to zero. In particular, what we have is that the expected value of xy equals the expected value of x times the expected value of y equal to 0. And so we have verified that indeed the variance of the sum is equal to the sum of the variances. Let us now look at some examples. Suppose that x is the same random variable as y. Clearly, this is a case where independence fails to hold. If I tell you the value of x, then you know the value of y. So in this case, the variance of the sum is the same as the variance of twice x. Since x is the same as y, x plus y is 2 times x. And then using this property for the variance, what happens when we multiply by a constant, this is going to be 4 times the variance of x. In another example, suppose that x is the negative of y. In that case, x plus y is identically equal to 0. So we're dealing with a random variable that takes a constant value. In particular, it is always equal to its mean, and so the difference from the mean is always equal to 0, and so the variance will also evaluate to 0. So we see that the variance of the sum can take quite different values depending on the sort of interrelation that we have between the two random variables. So these two examples indicate that knowing the variance of each one of the random variables is not enough to say much about the variance of the sum. The answer will generally depend on how the two random variables are related to each other and what kind of dependencies they have. As a last example, suppose now that x and y are independent. X is independent from y, and therefore x is also independent from minus 3y. Therefore, this variance is equal to the sum of the variances of x and of minus 3y. And using the facts that we already know, this is going to be equal to the variance of x plus 9 times the variance of y. As an illustration of the usefulness of the property of the variance that we have just established, we will now use it to calculate the variance of a binomial random variable. Remember that a binomial with parameters n and p corresponds to the number of successes in n independent trials. We use indicator variables. This is the same trick that we use to calculate the expected value of the binomial. So the random variable x sub I is equal to 1 if the ith trial is a success and is a 0 otherwise. And as we did before, we note that x, the total number of successes, is the sum of those indicator variables. Each success makes one of those variables equal to 1, so by adding those indicator variables, we're just counting the number of successes. The key point to note is that the assumption of independence that we're making is essentially the assumption that these random variables xi are independent of each other. So we're dealing with a situation where we have a sum of independent random variables, and according to what we have shown, the variance of x is going to be the sum of the variances of the xi's Now, the xi's all have the same distribution, so all these variances will be the same. It suffices to consider one of them. Now, x1 is a Bernoulli random variable with parameter p. We know what its variance is. It is p times 1 minus p. And therefore, this is the formula for the variance of a binomial random variable. We will now study a problem which is quite difficult to approach in a direct brute force manner, but becomes tractable once we break it down into simpler pieces using several of the tricks that we have learned so far. And this problem will also be a good opportunity for reviewing some of the tricks and techniques that we have developed. The problem is the following. There are n people, and let's say for the purpose of illustration that we have 3 people, persons 1, 2, and 3. And each person has a hat. They throw their hats inside a box, and then each person picks a hat at random out of that box. So here are the 3 hats. And one possible outcome of this experiment is that person 1 ends up with hat number 2, person 2 ends up with hat number 1, and person 3 ends up with hat number 3. We could indicate the hats that each person got by noting here the numbers associated with each person, the hat numbers. And notice that this sequence of numbers, which is a description of the outcome of the experiment, is just a permutation of the numbers 1, 2, 3 of the hats. So we permute the hat numbers so that we can place them next to the person that got each one of the hats. In particular, we have n factorial possible outcomes. This is the number of possible permutations. What does it mean to pick hats at random? One interpretation is that every permutation is equally likely. And since we have n factorial permutations, each permutation will have a probability of 1 over n factorial. But there's another way of describing our model, which is the following. Person 1 gets a hat at random out of the 3 available. Then person 2 gets a hat at random out of the remaining hats. Then person 3 gets the remaining hat. Each time that there is a choice, each one of the available hats is equally likely to be picked as any other hat. Let us calculate the probability, let's say, that this particular permutation gets materialized. The probability that person 1 gets hat number 2 is 1/3. Then we're left with 2 hats. Person 2 has 2 hats to choose from. The probability that it picks this particular hat is going to be 1/2. And finally, person 3 has only 1 hat available, so it will be picked with probability 1. So the probability of this particular permutation is 1 over 3 factorial. But you can repeat this argument and consider any other permutation, and you will always be getting the same answer. Any particular permutation has the same probability, 1 over 3 factorial. The same argument goes through for the case of general n people and n hats, and we will find that any permutation will have the same probability, 1 over n factorial. Therefore, the process of picking one hat at a time is probabilistically identical to a model in which we simply state that all permutations are equally likely. Now that we have described our model and our process and the associated probabilities, let us consider the question we want to answer. Let x be the number of people who get their own hat back. For example, for the outcome that we have drawn here, the only person who gets their own hat back is person 3, And so in this case, x happened to take the value of 1. What we want to do is to calculate the expected value of the random variable x. The problem is difficult because if you try to calculate the PMF of the random variable x and then use the definition of the expectation to calculate this sum, you will run into big difficulties. Calculating this quantity, the PMF of x, is difficult, and it is difficult because there is no simple expression that describes it. So we need to do something more intelligent, find some other way of approaching the problem. The trick that we will use is to employ indicator variables. Let xi be equal to 1 if person I selects their own hat and 0 otherwise. So then, each one of the xi's is 1 whenever a person has selected their own hat, and by adding all the 1's that we may get, we obtain the total number of people who have selected their own hats. This makes things easier because now to calculate the expected value of x, it's sufficient to calculate the expected value of each one of those terms and add the expected values, which we're allowed to do because of linearity. So let us look at a typical term here. What is the expected value of xi? If you consider the first description of our model, all permutations are equally likely, this description is symmetric with respect to all the persons, so the expected value of xi should be the same as the expected value of x1. Now, to calculate the expected value of x1, we will consider the sequential description of the process in which one is the first person to pick a hat. Now, since x1 is a Bernoulli random variable that takes values 0 or 1, the expected value of x1 is just the probability that x1 is equal to 1. And if person 1 is the first one to choose a hat, that person has probability 1 over n of obtaining the correct hat. So, each one of these random variables has an expected value of 1 over n. The expected value of x, by linearity, is going to be the sum of the expected values. There is n of them. Each expected value is 1 over n. And so the final answer is 1. This is the expected value of the random variable x. Let us now move and try to calculate a more difficult quantity, namely the variance of x. How shall we proceed? Things would be easiest if the random variables xi were independent, because in that case the variance of x would be the sum of the variances of the xi's. But are the xi's independent? Let us consider a special case. Suppose that we only have two persons, and that I tell you that the first person got their own hat back. In that case, the second person must have also gotten their own hat back. If, on the other hand, person 1 did not get their own hat back, then person 2 will not get their own hat back either. Because in this scenario, person 1 gets hat 2, and that means that person 2 gets hat 1. So we see that knowing the value of the random variable x1 tells us a lot about the value of the random variable x2. And that means that the random variables x1 and x2 are dependent. More generally, if I were to tell you that the first n-1 people got their own hats back, then the last remaining person will have his or her own hat available to be picked. That's going to be the only available hat, and then person n will also get their hat back. So we see that information about some of the xi's gives us information about the remaining xn, And again, this means that the random variables are dependent. Since we do not have independence, we cannot find the variance by just adding the variances of the different random variables, but we need to do a lot more work in that direction. In general, whenever we need to calculate variances, it is usually simpler to carry out the calculation using this alternative form for the variance. So let us start towards a calculation of the expected value of x squared. Now the random variable x squared, by simple algebra, is this expression times itself, and by expanding the product we get all sorts of cross terms. Some of these cross terms would be of the type x1 times x1 or x2 times x2. These will be terms of this form, and there is n of them. And then we get cross terms, such as x1 times x2, x1 times x3, x2 times x1, and so on. How many terms do we have here? Well, if we have n terms multiplying another terms, we have a total of n squared terms. N are already here, so the remaining terms, which are the cross terms, will be n squared minus n. Or in a simpler form, it's n times n minus 1. So now, how are we going to calculate the expected value of x squared? Well, we will use linearity of expectations. So we need to calculate the expected value of xi squared, and we also need to calculate the expected value of xi xj when I is different from j. Let us start with xi squared. First, if we use the symmetric description of our model, all permutations are equally likely, then all persons play the same role. There's symmetry in the problem. So xi squared has the same distribution as x1 squared. Then x1 is a 0-1 random variable, a Bernoulli random variable. So x1 squared will always take the same numerical value as the random variable x1. This is a very special case which happens only because a random variable takes values in 0, 1, and 0 squared is the same as 0, 1 squared is the same as 1. This expected value is something that we have already calculated, and it is 1 over n. Let us now move to the calculation of the expectation of a typical term inside this sum. So let I be different than j and look at the expected value of xi xj. Once more, because of the symmetry of the probabilistic model, it doesn't matter which I and j we are considering, so we might as well consider the product of x1 with x2. Now, x1 and x2 take values 0 and 1, and the product of the two also takes values 0 and 1. So this is a Bernoulli random variable, and so the expectation of that random variable is just the probability that this random variable is equal to 1. But for the product to be equal to 1, the only way that this can happen is if both of these random variables happen to be equal to 1. Let us now turn to the sequential description of the model. The probability that the first person gets their own hat back and the second person gets their own hat back is the probability that the first one gets their own hat back and then multiplied by the conditional probability that the second person gets their own hat back, given that the first person got their own hat back. What are these probabilities? The probability that the person gets their own hat back is 1 over n. Given that person 1 got their own hat back, person 2 is faced with a situation where there are n minus 1 available hats, and one of those is that person's hat. So the probability that person 2 will also pick his or her own hat is 1 over n minus 1. Now, we are in a position to calculate the expected value of x squared. The expected value of x squared consists of the sum of n expected values, each one of which is equal to 1 over n, plus so many expected values, because we have so many terms, each one of which, by this calculation, is 1 over n times 1 over n minus 1. And we see that we get cancellations here, and we obtain 1 plus 1, which is equal to 2. On the other hand, we have this term that we need to subtract. We found previously that the expected value of x is equal to 1, so we need to subtract 1. And the final answer to our problem is that the variance of x is also equal to 1. So what we saw in this problem is that we can deal with quite complicated models, but by breaking them down into more manageable pieces, first break down the random variable x as a sum of different random variables, then taking the square of this and break it down into a number of different terms, and then by considering one term at a time, we can often end up with the solutions or the answers to problems that would have been otherwise quite difficult.